Hi guys, this is Algebra 1, Lesson 7-4, Factoring Polynomials. In this lesson, we'll be able to factor a polynomial. Let's start with model and discuss. A catering company has been asked to design mailboxes for entries and side dishes. The sections for the side dishes are half the length and width of the entry sections. Okay? The sections for the entries must be square. Okay, so you're going to put the sections for entries and side dishes so that you design a mailbox that meets each of these requirements separately. So let's look at part A.A. Equal numbers of sections for entries and side dishes. So you want equal numbers of sections for entries and side dishes. So numbers. It doesn't have to be the same area. But we want the same numbers of entries and side dishes. So we know that the sections for the side dishes are half the length. So in order to if you have two side dish boxes, then that means you can put one entry right next to each other, right? So you can maybe have a lunchbox that has two side dishes and then a big meal. Or you could have a bigger lunchbox where you have two meal boxes with two side dish boxes, right? So that would give you an equal number of sections for entries and side dishes. Okay? If you have bigger ones, you can even have that is side dish. You can even say, you can have 1, 2, 3, 4 side dishes, and then add 1, 2, 1, 2, 3. Oh, it doesn't really work that way. What if in order to get 4, how do we frame that? 1, 2, 3, 4, and then we can move it vertically. Does that make sense? So it needs to have equal number of sections for entries and side dishes. So this could be A. Okay. And then what if we want more sections for entries than for side dishes? Then we can have 1, 2 side dish, but we want more entries. So we can have 1, 2, 3 entries. Okay? Or you can have 1, 2, 3, 4 entries and 5 entries, and then maybe 4 side dishes here. 1, 2, 3, 4, right? In a box. So there could be many options how you can design the lunchbox depending on the shapes of your lunchbox. Okay, so that is A, B. What if we want more sections for side dishes than for entries? So we want more little green boxes, right? So we can maybe have 1, 2, 3, 4 side dish sections and just 1 section for entry. Okay, for a lunchbox. Or you can have multiple. So like 8 side dishes and then 2. So the idea here is that you have a proportion for the side dishes and the entries, right? So for each mailbox from part A, we're going to write an algebraic expression to model the area of the mailboxes. How do we write these as an expression? What if the bigger mailboxes are representing X, right? And then the smaller one, side dishes, would be ones. just like our algebra tiles. Then for this one, we can have 4x plus 4 as an expression, right? For this one, if we want to continue representing the same tiles, we can have 2x plus 2. That would be x plus 4. That would be 5x plus 4. That would be 3x plus 2. There we go. Yeah. Or if we want the entry sections to be x squared, then we can have 4x squared plus 4x, or depending on what they represent. Okay? Let's look at an existential question. How is factoring a polynomial similar to factoring integers? So today we will factor polynomials. And in order to do this, you need to know and be comfortable with factoring integers first. So think about greatest common factor when you've learned factoring the integers. Let's look at example 1. Find the greatest common factor. What is the GCF of the terms of this polynomial? How do we figure out the GCF of a polynomial? Well, think about the GCF for integers. How do you figure out the GCF of integers? So look at all your coefficients, 12, 8, and 6. Figure out the GCF. It would be 2. 2 is your GCF. You also have to look at your variables. You have x to the 5th power, x to the 4th power, and x to the 3rd power. For each term, you need to break it into the coefficient and the terms, okay, the variables. So the coefficient, you figure out the GCF for the coefficient, then you figure out the GCF for the variables, which is going to be x cubed for this. And you can now say the greatest common factor for these terms would be 2x cubed. Okay, this is very important because that's going to be used to factor out our polynomial. So first, let's practice finding GCF of the terms for each polynomial. Let's try to figure out GCF for A and B. Pause the video, come back when you are ready for answers. All right, are you ready? Look at the coefficients for these terms, 15 and 18. What is the GCF for 15 and 18? You have to factor 15 and 18 out. If you factor it out, 15 is a product of 3 and 5, right? 18 is a product of 3 times 6 and 3 times 2, right? So 3 times 3 times 2 would be 18. And so the GCF would be 3. Look at the variables. You do not have a variable on the second term. What do? You don't have a GCF for the variable, and that's fine. Okay, so the GCF for both of these terms would just be a constant 3. Okay, part B, negative 18y fourth, 6 plus 6y cubed plus 24y squared is our polynomial. We have 3 terms total. Look at their coefficients and break them down into factors. 18 is divisible by 2 times 9. 9 divisible by 3 and 3. So 2 times 3 times 3 is 18. And then 6 is 2 times 3. 24 is 2 times 12. 2 times 6. 2 times 3. So 2 times 2 times 2 times 3 is 24. We see 1 2's in all of them and 1 3 in all of them. So your GCF would be 2 times 3, which is 6 for the coefficient. Do we have GCF for the variables? Yeah, y fourth, y third, y squared will give you a GCF of y squared. So your GCF of the entire polynomial would be, for each term, would be 6y squared. Okay, that's how you get the GCFs. Alright, let's go to example 2 on the next page. Factor out the greatest common factor. So now, why did we learn how to figure out the GCF for each term in the polynomial? Why is it helpful to factor out the GCF from the polynomial? So first, let's look at this example. Negative 12x cubed plus 18x squared minus 27x. The GCF for each term would be negative 3x. Okay? That means we can factor out the GCF from each term. That means we're going to divide each term by negative 3x and figure out a more simple version of a polynomial, and then we can just multiply all of that by the greatest common factor, and that's still going to equal our polynomial. Does that make sense? So if we factor out negative 3x from negative 12x cubed, we get 4x squared. So if we multiply negative 3x times 4x squared, we get our first term. And then we factor out negative 3x from the second term, 18x squared, we get negative 6x squared. Negative 6x. And so if we multiply negative 3x times negative 6x, we get positive 18x squared, the second term. Does that make sense? And so if we factor out negative 3x from negative 27x, we just have 9. And so if we multiply negative 3x times 9, we get the third term here. So we're going backwards and factoring it out so that we have a parentheses and we have a form where we could use distributive property. So factoring out the greatest common factor results in a polynomial with its smaller coefficients or smaller exponents of the variables. This is when you want to factor the polynomials into pieces, into smaller numbers, so that you can see what's really in there. Okay? It makes it easier to analyze the polynomial and factor it even further. So let's look at try number 2 and practice factoring out the GCF from each polynomial. You don't have to factor it out completely. Just factor out one GCF. Okay? There's only one GCF for all three terms here. Okay? Figure out the GCF and factor it out. Pause the video. See if you can do it by yourself. Come back when you're ready for answers. Okay, are you ready? So the greatest common factor for part A. Look at the coefficients. What if you do not have a coefficient for the first term? Then you don't have a greatest common factor because your coefficient is 1. And so GCF for 1, 5, and negative 22 would just be 1, right? So GCF would just be 1 and then your variable, GCF for your variable. So your variable has x as variables, right? So x cubed, x squared, x, the GCF for that one is x. So your GCF for the entire polynomial would be x, so factor x out. X times x squared plus 5x minus 22 will result in our polynomial. Part B, what is the GCF for all these coefficients? 16, 28, and 20, the GCF for that would be 4. Okay, and then the GCF for the variables would be y cubed. That is the smallest power we have. So because we have two negatives, let's factor out the negative as well. So we can say the GCF would be negative 4y cubed. And if we factor that out, make sure you change the negative into positive because you're factoring negative out, which means you're taking the sign out. So if it was negative, it becomes positive. If it was positive, it becomes negative. It becomes your opposite, okay? So if you factor that out, you get 4y cubed minus 7y plus 5. All right. Check your answers, see if you got them right. Let's look at our last example application. Factor a polynomial model. Elani is in charge of marketing for a travel company. She is designing a brochure that will have 6 photos. The photos can be arranged on the page in a number of ways. So look at these photos. There are 2 main square photos which have a length of x inches on each side. And there are 4 narrower photos that are each 1 inch by x inches. We don't know what x is, right? But yeah, it looks like these photos are connected, but we're gonna have two main square photos and then narrower photos by the sides. So what is the total area of the photos? First, we need to find the area of each type of photo, right? So the total area would be the area of the square photos plus the area of the narrower photos altogether. So we have two square photos. We're going to multiply x squared by 2 because each side would be x, right? And the area of the squares would be x squared. So 2 times x squared plus area of narrower photos would be 1 times x, right? So we have 4 of those narrower photos. So we're going to multiply 4 times 1x. And so the total area by expression would be 2x squared plus 4x inches squared. That is how we can represent expressions in real life. Let's find the rectangular arrangement for the photos. What factored expression represents the area of the arrangement? So we're going to try placing the photos in one row. And the arrangement has a height of x inches total. Right, they're all x inches high. The arrangement has a width of 2x plus 4 inches. So yeah, if we factor 2x squared plus 4x, we get x times 2x plus 4, and that gives us the height. That gives us the different dimensions, right? The height and the total length of these photos all together. So the factor form gives you different dimensions. That is why it's helpful to factor the polynomials out in real world. Let's factor out the GCF from the polynomial. What does the GCF represent in this situation? So the GCF is actually not x. The GCF of the polynomial would be 2x. So if we factor them out, we get 2x and x plus 2. What does this mean? It means that the arrangement, could be where you have 2x as the height and x plus 2 as your other side of dimension. So if you have 2 rows, that would give you 2x, right? And so if you have 2 rows of x heights, then the arrangement will have a width of x plus 2 in total for the width. So the GCF represents the height of one possible arrangement of the photos. It doesn't have to be the height, but it just gives you one choice of how it could be arranged in an order. Alright, so which of these two arrangements is a more practical use of space on a page of a brochure? Right, look at this one. Look at the top one. The top one is longer horizontally, right? The bottom arrangement is more rectangular, which is closer to a paper size, right? A regular paper size. So the second one would be more practical. Because the arrangement with the photos in one line will likely be too wide for one page to be printed out. Right? So looking at different arrangements with different expressions will give you some options, and looking at those options, you'll be able to determine which one would be more practical in this scenario. So let's look at try number 3. Suppose the dimensions of the narrow photos were increased to 2 inches by x inches instead of 1 inches by x inches. What expression would represent the new arrangement based on this GCF? So change the expressions to fit the new dimensions. Pause the video, see if you can do it by yourself. Come back when you're ready for answers. Alright, are you ready? So instead of 1 inch, it would be 2 inches. And so you have, but your squares are still the same. So the big squares are still the same, right? So they're going to be x by x, but the smaller would be 2 by x. You have 4 of them. So your expression would be 2 times x squared plus 4 times 2x, which will give you 2x squared plus 8x as your total area, right? If you figure out the GCF of this would be 2, right? GCF for 2 and 8 would be 2. GCF for x and x squared would be x. So GCF for the polynomial would be 2x. If you factor that out, you get 2x times x plus 4. And so that would give you the arrangement based on the GCF. Check your answers. Okay, let's summarize our concept. We learned how to factor polynomials. So in order to figure out how to factor polynomials, you need to figure out their GCF. Your GCF for a polynomial would not only be the greatest common factor for the coefficients in numbers, you also have to figure out the greatest common factor for the variables. So if you have multiple variables like the example shown, you will have to see if there are the same variables for each term. So in this case, y is not in your third term, so y is not your part of your greatest common factor. But each term has one x at least, right? So your greatest common factor would be 3x in this case. But if you have one y on the third term, then your greatest common factor could be 3xy. It just has to have the variable in all the terms, okay? So depending on your power, that means your power tells you how many variables there are in each of your terms. So the least number of power for each variable would be counted in your greatest common factor. All right, if you have any more questions, please feel free to ask Ms. Kang in class. Otherwise, we'll continue with the next lesson, lesson 5, about factoring x squared plus bx plus 6 in the next video. Thanks, guys. Bye.